It's a real pleasure today to be able to introduce Dr. Alexander Wolfe, who will be talking about the Anthropocene from the geological perspective in terms of how do geologists view time in the subdivisions of time, and so get us started really to think about the Anthropocene. So I first met Alex when he was still a PhD student, because we were both working in the Eastern Canadian Arctic, where I'd worked for a long time, and Alex was looking at lake sediments, and so were we. And Alex had this weird thing. He was looking at these really youngest stuff, and I was mostly interested in the longer record of watching the evolution of climate over thousands of years. And Alex always wanted these high resolutions at the top of the cores, and I wondered what was really what motivated him that much. But he quickly showed me that, in fact, everything's changing right now, and you can see it basically in the geological record that's preserved in lake sediments. And so once he completed his degree, I said, you got to come over to Boulder. And so he came first as a postdoc and then as an independent scientist, and spent 5 years here on campus. And he and I spent quite a few really fine field seasons together, working together in the Canadian Arctic. But Alex is a paleoecologist. I know him best for his work on the recent time scale, the Quaternary, but he's been working on early in the Cenozoic. He's worked on the Cretaceous things. So he has a really broad perspective. And he then got invited to work with a large group of people that's known as the Anthropocene Working Group, which was tasked with trying to provide a geological perspective on what do we really mean by the Anthropocene. And so with really no further ado, I'm going to turn it over to Alex. He's got a PowerPoint. He'll bring that up on a shared screen.
Yeah, I haven't done that much Zoom lecturing, just a little bit for a course I was teaching on Arctic environments last term, and it is very different. So bear with me. I'm going to talk about this debate really that's ongoing that I've been involved in, is whether the Anthropocene merits to be recognized by my discipline, the earth sciences, as a formal subdivision of geological time, and what the implications of that might be, or whether, as some of my colleagues think, this is a sort of misguided interpretation of what the stratigraphic record, which is really the formalization of geological time, and that we're misinterpreting its overarching objectives in establishing, in wanting to establish a formally recognized subdivision of geological time, then that would rival things like what Gifford was referring to, the Eocene and the Cretaceous and so on and so forth. So I'm going to walk us a little bit through the concept to show that, at least conceptually, the notion of Anthropocene is not a new one, it's an old one. It goes back several hundred years, this idea of humanity somewhere at the center now of Earth system functioning. And it's not a novel idea at all. I'm going to talk a little bit about the Anthropocene Working Group has done as an officially sanctioned group within the International Commission of Stratigraphy, and in particular, the subdivision of that deals with the Quaternary, which is the last 2.5 million years of Earth history. I'm then going to show some examples, various examples, to try and get our thought patterns going. And then, I've pulled back from my formal involvement with the Anthropocene Working Group, not because I don't think they're tremendous scientists and just wonderful people to work with, and absolutely very diverse, largely indefatigable, but really it's actually my own ego, my weakness of not really being able to handle the outright criticism which had begun. I'm half retired now, and so I try and avoid the things that I don't really like, and I don't like vitriolic attacks, and that's where this was going. And so I pulled back. In 2016, the term Anthropocene, and of course, many of my leading colleagues running the Anthropocene Working Group now are Brits, and they say Anthropocene. And we say anthropogenic, we don't say anthropogenic, but anyway, I guess the North American pronunciation would be Anthropocene. And the Oxford Dictionary has an entry whereby this denotes the current geological age, the period during which human activity has been a dominant influence on climate and the environment. Okay, that's a little bit different from saying that humanity is a dominant influence on the nature, structure, and composition of the geological record. Okay, so that's worth noting. And so early 21st century from anthropo, well, you get it, anthropology, people, from the Greek. But conceptually, this notion is not a new one. If we go to the great naturalist, the Comte de Buffon, in his time, so now we're talking about the early mid-18th century, the father of paleontology, you know, in the heyday of the natural sciences, he recognized something which he called la septième époque de la nature, the seventh epoch of nature, which indeed is nature under the influence of humanity. So obviously he was taking cues from the progression of animal husbandry and agriculture, and said that, well, you know, this is real. It's not just humanity as sort of passengers on a natural system, it's humanity as a driving force for many of the processes that Buffon was interested in, one of the first people to consider things like population dynamics and so on. The French/Italian cartographer Antonio Stoppani had a term called the Anthropozoic, which recognizes the same thing that Georges-Louis Leclerc, Comte de Buffon, and perhaps most famously, Vladimir Vynarsky, the Russian philosopher of science, who coined the term biosphere. He also had this inkling of something called the neosphere, which was then, you know, sort of on this voyage to the omega point, whereby this was a world that was truly under the dominion of the human enterprise. From the natural sciences, the Irishman Tyndall and the Swede Arrhenius, who are starting to explore the notion of greenhouse gas. And so, of course, that's any gas that is capable of absorbing infrared radiation, so the characteristic wavelengths in the near infrared emitted from objects that are, you know, around 290 Kelvin, for example, the Earth. So the Earth's radiation is retained by certain gaseous species, and Tyndall was one of the first to explore this with early adventures in spectroscopic measurement of energy transmission through vacuum bells, which he filled with different gases, including carbon dioxide. Arrhenius, really the father of physical chemistry, building and collaborating with Tyndall and Tyndall's ideas, even predicted, again, not with any anticipation of whether this was good or bad for humanity, but, you know, he recognized that CO2 was emitted by things like combustion, and that CO2 was likely to increase in the atmosphere, and that this would have the potential to modify climate as a consequence of the properties that Tyndall was describing. And so really, this idea is not a new one. It's got a couple of centuries of circulation in the literature, both from the humanities as well as the natural sciences. But it really took the turn of the last century or the last millennium to the present one, before Gene Stormer, who's a limnologist, he actually comes from my field in diatom paleoecology, sadly missed, and Paul Crutzen, who's an atmospheric chemist, they began touting the term Anthropocene, and it turned out to be an example of the right place at the right time. And so beginning really with this opinion piece. So this is a paper with absolutely zero data, you know, kind of like most Nature papers, not just kidding. So a paper published in Nature, very, very short, very topical, and very provocative, where Crutzen pens, it seems appropriate to assign the term Anthropocene to the present, in many ways, human-dominated geological epoch, supplementing the Holocene. Now, of course, humanity has been active through the Holocene and through the late Quaternary, certainly. Civilizations, animal husbandry, agriculture, all developed over timescales of millennia, not the most recent decades. But still here, the present would then supplement the Holocene, the period of the last 10, 12 millennia, that's since the last ice age, which has had relatively equable climate conditions, which have in part allowed for this astounding trajectory in the human enterprise. And it's really with that paper, the traction now of the term Anthropocene began to take off. And so everybody wants a piece of the Anthropocene. New journals, left, right, and center. So this is just an example. I haven't updated this in a couple of years, but so at least 3 journals and books and everybody. And then we now use bibliometrics. And so this bibliometrics, I did it and I published it and I haven't updated it because it's such a pain to do in the first instance. But we see this trend, from say around 2000 when the word shows up, 2002, Crutzen's Nature paper, and then very rapidly within a couple of years, the term is being used all over the place, and that can be tracked bibliometrically, not simply in the geosciences, but also in ecology, the environment, archaeology, all these other disciplines, some of them cognate to the earth sciences, some of them less so. And it can't be reined in. And I think that's great. It's right term, right place at the right time. The only problem is if you ask a medical scientist, a legal scholar, a geologist, an anthropologist, an artist, what they think of Anthropocene, what they think the term means, you're likely to get a different answer. And so semantically, I just put, this is out of date, but I've been publishing papers, essentially since I met GIF, which is half my life. I'm 54 now. And I have never had papers get cited as rapidly or as immediately as any of the papers I've written on the Anthropocene. 3/4 of my citations ever in my career are all based on these few papers, none of which have really resolved anything. And so in a way, perhaps cynically, you look at these trends and you wonder, is this a response to the Anthropocene, or is it indeed a symptom of what the Anthropocene is all about, which is this ever accelerating multidimensionality of the human enterprise and how that gets inscribed into our conscience, whether our conscience is that of an ecologist, a historian, or an earth scientist. I view that with the term Anthropocene, that etymology with the scene at the end, which is like Holocene or Pleistocene or Eocene, it's the vernacular that Crutzen used, which relates it closely to the earth sciences. And so earth sciences may have a responsibility to try, as the primary rationale for studying the Anthropocene, as trying to attain a unifying definition which we can all accept across disciplines. Okay, so that's really was my motivation to get implicated in this. But the point that I'm just trying to make with this protracted introduction is just that, the idea that this is a brand new concept just dropped on us because of time and place, that's not true. Many scholars have been thinking about the nature of humanity's footprint now for not decades, but indeed centuries. It's just the timing was right. And here's the point that I just made. The Anthropocene means many things to many people and communities. And so wouldn't it make sense as global scholarship to have one definition, and one definition that everyone could work with? And so just as an example, I'll take my colleagues in archaeology, and Gifford and I have worked over the years with a number of archaeologists and geoarchaeology and science-based archaeology, which is called archaeometry, which relates to what GIF does, which is geochronology, dating stuff. And it's really interesting, for them, it's like Anthropocene, well, that's the first time you get a gnawed mammoth bone or a hearth or the first inscription of human influence on the landscape. You take Clovis, New Mexico, or something like that, or some of the areas, some of the beautiful sites that are in the caves and other repositories around the Front Range, the South Platte Valley, and so on. And your earliest signs of humanity, that's the Anthropocene. I would argue against that. I have a different view, which is, it's not so much the human influence, it's when humanity truly starts exerting dominance at a planetary scale, where we've emitted enough stuff into the environment, into the atmosphere, to fundamentally modulate now the physics, biology, and chemistry of the planetary whole. But you can see, very rapidly, just with archaeologists who are relatively close to my field because we use the same tools, we enter into this semantic issue. Now, how about then if I were to speak to, so there's a death metal band called Cattle Decapitation, and they have an album out called The Anthropocene Extinction. Now imagine I cozy up to the lead singer of this band and we start talking about Anthropocene. We're clearly going to have a different nature of definition. And I strive, and I think I speak on behalf of some of these individuals, I'm striving towards trying to help the situation along by at least having a unified semantic, a unified definition for the term Anthropocene with which we can move forward. And so the working group then is, this is where we didn't receive any funding, but a group was assembled surrounding this man, who's a paleontologist from the University of Leicester in the Central Midlands of the UK, Jan Zalasiewicz, and he's lots and lots of experience in stratigraphy. He's worked quite a bit in the Quaternary as well as in the Ordovician. He's a paleontologist by training. And there are many other names from across the disciplines, many Americans, a couple of Canadians, and a bunch of Brits. And we've been working to try and explore this concept, trying to define the Anthropocene, what it might mean, and whether we can use the auspices of stratigraphy, which is the formal science that names and identifies and follows strict protocols to define the various units of geological time, whether or not the Anthropocene fits within that schematic framework or not. And essentially the group stood a couple of years ago when I backed away. We have a supermajority amongst us that yes, we should go forth. Yes, it should be named. Yes, it should be probably around the middle of the 20th century for a series of reasons. But that's when conservatively you could truly demonstrate on many different lines of evidence that by that time, so we're talking about the immediate post-World War II world, that humanity has really sort of started taking control of some of the fundamental reins of the energy balance, atmospheric composition, ocean chemistry, and some of those other notions that we were discussing right before the talk. We try to do this, however, without getting, carried away or, seduced by recent releases in death metal that exploit the term Anthropocene, to their credit. Rather, we try and be dispassionate and objective and not entertain whether, the Anthropocene is, sensationalist, ushering in of the end of the world. And, we've really screwed things up now. And, damn, we should have voted for Ralph Nader 30 years ago. It's not at all like that. It's just an attempt. I certainly do have my feelings. I'm a very emotional person. But in my work with it's just like, okay, can we objectively see changes in the structure of Earth materials that correspond with a change in the dynamics of the planet that are inscribed reproducibly and permanently in the geological record, which is being formed every moment of every second and has since the beginning of the Earth 4.5 billion years ago. So that's sort of how we do, whether we succeed or not. And so that's a sort of an introduction to what we're all about in the Anthropocene Working Group. And so this is the latest edition of the geological timescale. So it's 2 books. And in the books, it's got descriptions of rock units, you know, the Landovarian and the lower Ordovician, and they're all divided elegantly into ages and epochs and periods and eras, and the type localities, or the most elegant expressions, or oftentimes the best studied expressions of each of these intervals of the last 4 billion years of Earth history are subdivided and described with references and so on. And in 2012, the Anthropocene made a sneak appearance as a currently informal term to signify a contemporary time interval. So the beginning of recognition amongst the chair people and the keepers of the geological timescale. These people are, yes, they're regular geologists, but they're also from this subdiscipline called stratigraphy. And stratigraphy is very, very serious about this idea of classification and the nomenclature, and indeed the typification of the rocks that make up the geological record, whether it's the recent one or the distant one. And so the question is, you know, are they open to it or are they not? Is this something where we're going to have to do, you know, mortal battle, or is it so plainly evident, or is it just not worthwhile? Is it, as my title slide says, is it fanciful folly? For this document, which basically looks like this summarily, is quite preciously kept by many geologists, perhaps akin to something like the periodic table to the chemists, or the laws of thermodynamics to the physicists, or various theorems in mathematics. Perhaps not to all earth scientists, but to those who are deep in the record, this is a very, very key document in terms of, you know, Toarcian and biogeochemical, you know, those are very, very different. To most of us, it doesn't really matter. The question is then, if right up here at the very, very, very top of the Holocene, whether a little skiff, maybe 1 pixel thick, would merit the identification as the Anthropocene within the formalized stratigraphic chart that we have in front of you. To do that, supermajority is needed at various different levels. So SQS is quaternary stratigraphy, and then the International Commission on Stratigraphy, and then finally the International Union of Geological Sciences would have to approve these by supermajority at each increment once the proposal is made, and the proposal would proceed conceptually, but then would also include these, what we call type localities, or golden spikes. It's called the golden spike because it's a GSSP, a global stratigraphic something and point. I can't even remember what it is, but it's called the golden spike colloquially. And this would be the place which would precisely identify the transition then from a Holocene to Anthropocene. Now, when we move from stratigraphy, I'm just checking my time. Gift, you'd cut me off at any time if you want to move. What time do you want to move to questions? Maybe 10 minutes or so?
Yeah, 10 minutes would be good.
Yeah, okay. And so if we move from stratigraphy to this more dynamic and evolving branch of earth science, which we call earth system science, which is considering really the dynamics of how things work, I think we can prove quite readily that the physics of the planet, the chemistry of the planet, the biology have changed remarkably in the last century, but in particular since the middle of the 20th century. It's driven, in essence, by not quite exponential, but the rapid growth in human population. For example, human population has literally doubled in the time that I've known Gifford Miller. This is astounding. And with that population growth, there's been an increased proportion of that population that lives in urban environments as opposed to rural environments. And when you live in urban environments, you are essentially involved in the manufacture and trade and exchange of goods and services, which have a very, very pronounced carbon footprint, because then you have to move those services around the planet. And it really is, you could say that with the globalization of economic systems, with things like Bretton Woods and all these reorganizations and the IMF after the Second World War, that really that is in lockstep with the environmental and indeed demographic patterns that we've seen at the planetary scale. The question then becomes not whether there is biological, chemical, and physical signature, because we know that this has occurred from the perspective of dynamics. It's whether it is meaningfully inscribed then as geological materials in the bottom of oceans, in the bottom of caves, in the bottom of lakes. Is it identifiable? Is it something that we could then, for example, map? Because that geological timescale that I showed you before, one of the reasons it's so coveted by geologists is because, a lot of our students, well, maybe less, now most of them are unemployed, but there was a time when most of our students would go out and get jobs mapping, for example, in petroleum and stuff. And mappability ends up, for the practical geologist, being of fundamental importance to the application of the timescale. Can you map deposits associated with the Holocene? That's a good question. Where would you have to go? How would you do that in Boulder Creek? So there's a lot of things to think about here. And of course, the changes, this of course is the Keeling curve. And so we're now, as you know, 30% or so above the natural background in terms of carbon dioxide. There's also nitrous oxide. There's also methane. There's also a host of chlorofluorocarbons and other radiatively active gases. So much so that when the true experts in climate modeling put these concentrations together and express them as watts per meter squared, or units of energetic force retained per unit area, as opposed to evading to the atmosphere as it would in a thermodynamically balanced planetary system, we see that there's an energy imbalance from all the stuff that humans have put into the atmosphere, closing in on 1 meter per every meter squared. And that's now every meter square on the entire planet. So it doesn't seem like a lot of light bulbs when you think about it, but when you think about at a planetary scale, and then of course we can start to comprehend why things like Arctic sea ice and continental glaciers in the Arctic and Antarctic are melting so rapidly. Of course, we now know from the Argo Buoys program, which is monitoring the temperature of the deep ocean, which really serves as a heat capacitor for our planetary system, that about 90% of this excess energy, this close to one watt or joule per second per meter squared, most of it goes into the deep ocean. And what we see as warming on the surface, maybe 1 degree, is really only about 5% or so of this total energy surfeit. And so we have this energy imbalance. And I was asked before the talk as to, well, if we stopped everything right now, how long before things would go back to normal? And I think, Gifford and I were mentioning that, well, our view from the modeling is that we're talking about, probably millennia, simply because there's so much of this accrued energy stockpiled in the deep ocean. So these are the temperatures, things are warming, and that's just touching the tip of the iceberg. That's just touching really the carbon cycle and a few chlorofluorocarbons, the few of these gases that are radiatively active, the ones that Tyndall and Arrhenius were studying hundreds of years ago in their laboratories. When we look at the rest of the periodic table, and we try and compare these in terms of, well, how big is the human disruption of the carbon cycle? Turns out that it's maybe 10% out of whack from what it would normally be with this excess CO2 emitted by human activities. compared to other fundamental planetary cycles like that of nitrogen, where we now manufacture biologically available nitrogen through industrial processes. That's how we make fertilizers and so on. And we look at the rest of the periodic table, you know, most of the naturally occurring elements have fluxes, you know, which is the number of moles per unit volume, per unit time, that are greater, fluxes associated with human processes that are far greater than their natural fluxes associated with the sum total of subduction. That's when you melt rocks to make magma and volcanism and tectonics. All these natural processes actually turn out on a mole per mole for these elements that you see in red, which is most of them, to be dominated on a molecule by molecule basis by human processes. For example, construction, for example, erosion, both deliberate erosion, that's sort of like the erosion that the US Army Corps of Engineers does, or non-deliberate erosion, when, for example, we open up new areas for agriculture, for example, in the developing world, which actually this unintentional erosion and the associated movement of matter is far greater than that which is intentional at the planetary scale. So it turns out that, you know, we're moving the chemistry, we're moving the physics, and we're moving the biology in, by any geological standard, we're doing this in very, very rapidly ways that are directly, can be tractably associated with the acceleration of human activity. Most common bird on the planet today is Gallus gallus, the common chicken. There's about 3 chickens per person, so 7.5 billion. Well, so yeah, it's like 23 billion chickens on the planet. That's a lot of ecosystem mass for birds. And so yeah, other birds are suffering. For example, wild ones, where their habitat is removed, to create what? Chicken farms or beef farms. And so the collapse of the animals, you know, from the very small to the very large, we have less of a good handle on the microbial world, which is in many ways more important, you know, not to people and not to funding, but in terms of process and the microbes are very, very important. But we do know that large, furry, fluffy organisms, many of them with good fossilization potential, are in trouble at the expense of, you know, the winners in the game, which is things like the chicken. If you think this looks like being a biological winner, I'm not so sure whether that's a winner or loser, but I'm just trying to use ecological terms. Right over here, Diomeda exulans, that's a wandering albatross, and this animal, it's a chick that has perished, and the chick has perished because the chick is 50% by mass plastic. And so when it fledges, it's got too much plastic. I think there's a couple of cigarette lighters in there and maybe some condoms or something. It's too heavy to fly, so it can't fledge. And so these birds that have been, you know, flying around Antarctica on their annual cycles you know, only setting foot on land to nest, well, you know, if you fly for a living and you're full of cigarette lighters, you're probably going to go extinct. And that appears to be what's happening with some of these biospheric crises. These are just examples to show them this unintentional versus intentional movement of material, tonnage of material. This is from a retired glaciologist by the name of Roger Hooke from the University of Minnesota. And this is out of date. The numbers have been updated, but this is still the original where he has really coined this term anthropogeomorphology, to show then, if we go to the next slide, that if we have a background average here of, you know, somewhere around 10 millimeters a year, or tons of erosion, this is the average background Earth surface denudation. So the amount of material stripped from the Earth on average over the Phanerozoic, that's the last 500 million years, or the period of time where we have multicellular life for sure on the planet, that in, you know, essentially since about the 14th century, moving up towards the present, the total amount of materials moved by humanity, both intentionally and unintentionally, is greater than the average background of the tectonic and fluvial and glacial and wind-driven flux of Earth materials, according to Hooke's calculations. And this has been followed up by other people, including most famously David Montgomery at the University of Washington. So what are the proximate forcings? Well, like I said before, it's population, and it's population that is migrating. You know, now for the first time in humanity, we have a greater population in urban centers as opposed to people living in the countryside, leading rural existences. That has profound implications for economics and economics ties with energy use, and that scales actually with the temperature record and with the emission of anthropogenic greenhouse gases. So do we see this in the rock record? And I realize I don't want to go on too long. Is that, yeah, you know, like Giff said in my introduction, I was interested in the top little bit, largely because it was easier to collect. And Giff is a real animal in the field. And so he's good at collecting the stuff that's hard to collect. And that's the stuff that's way at the bottom when you've got to really test your equipment and your physical and mental game to get these deeper samples. And I was a bit of a wimp, a fair weather person in the field. And so I was happy with the top 5 centimeters. Of course, both stories go together, because if you have the longer record, it gives you a broader context of temporal variability in the system before humans come on stage. For example, how did these systems change at the end of the last ice age? You know, there was significant warming there. We melted 120, you know, the planet melted 120 meters of sea level equivalent in a matter of 3,000 years. That's pretty big warming. How does that compare to the current warming? And it turns out, so then we have a deeper geological record where we can always compare. And what we really see in the recent geological record is things are different. The biology, whether you look, well, just the nature of the sediment. So these are some of the places. That's actually Gifford Miller's finger and his arm. And here we have something that looks gray and something that looks black. Essentially, these are all cores of lake sediments taken from far field localities in the Arctic and in the mountains. There are lakes in the Front Range that look a lot like this. And what's happened is that the glacial influence with the melting of the glaciers has disappeared. The lakes have ceased producing a mineral sediment, which is this gray stuff, and started producing a sediment, which in geology we call a sapropel, or an organic sediment that has fundamentally different sedimentary qualities. And so that's sort of like what the Anthropocene rock record being built may look like. We have differences in the fossil content, whether it's pollen grains, or I work on these little things. They're called diatoms. They're unicellular algae. These are data from the mountains, because that's where I used to work. So Rocky Mountain, which is now burning. And then some sites in Montana, and there are sites in the Alps. We have sites all over the world that show this change there, where in, you know, especially, again, time and time again, these changes begin somewhere around the middle of the 20th century. And they accelerate into the present. And we would say that, oh, this is pretty good fossil record. You know, we had this changeover in species composition of the organisms which form the primary producer in these lakes. And, you know, it's inscribed. The sediments look different organic content, different fossil content, and in many cases, novel fossils altogether. For example, this right here is an electron micrograph of a combustion fly ash particle. There are some similar things that come from natural forest fires, but those ones typically have vestiges of the cellular structure of wood. These ones that come from the petrochemicals have this sort of gnarly surface texture because they're burnt. The burning occurs at such a higher temperature. And then these holes, these pitting, come from the degassing of the volatiles within the hydrocarbon. So they're distinctive, and they don't occur at any other time in the geological record. And so these are dozens of lakes. This is from my colleague from the UK, Neil Rose. So these are SCP, sedimentary carbonaceous particles. It's basically the fly ash. Once again, they come up, they start occurring in great concentration in the middle of the 20th century. Same thing with mercury, same thing with the signatures of organic nitrogen within the sediments. And we think that this is tracing the dispersal all over the Arctic and all over the Arctic and alpine lakes that we've cored, the dispersal of nitrogen that originates either from the burning of fossil fuels or from human manufactured agricultural fertilizers, because fertilizer is cheap, so people tend to over fertilize, then it gets volatile. This is what happens, this is what comes out of your feedlots, and that's why the lakes in Rocky Mountain National Park are changing in terms of their biology and their productivity, even though the sources are downwind, not upwind, but that's something to do with the upslope meteorology and so on. But we see this trend up.
Why don't you wrap up here and give us, so we have a little bit of time for questions.
So just another example of the geological materials. This is the Basque Coast. And so these are recent rocks with, bits of plastic and bricks, and the bricks, this is close to Bilbao. And then microplastics, landfill. There's a whole story. And what we would suggest is that indeed this geological record exists. We have a very, very convenient marker, which is a radionuclide marker. So we have sediments that begin to get radioactively hot as a result of experiments such as Trinity in New Mexico, July 16th, 1945. We start seeing measurable excess radiocarbon and plutonium and americium and cesium, which then provide us with these sort of razor sharp inflections. So here we're just going down core. And what we would entertain then is that it is the concentration of these, by definition, anthropogenic radioactive materials, which then provide us with the timeline for the beginning of the Anthropocene, whether you're in Antarctica, whether you're in the Front Range, whether you're in Manitoba, anywhere. And in some places, the sedimentary record is going to be pretty meager. In other places, it's going to be several meters or even tens of meters. But you can identify it, you can map it, you identify it using these criteria. We have ancillary criteria, so the geochemical basis, but we also have the lithology, which is the character of the rocks themselves that I showed before. Those proto-rocks, but those will be rocks at some point. And so we find compelling arguments that this exists in the geological record, that it's not a mere transient that's going to go away, that it scales very, very well with, that it compares favorably in terms of the desired criteria that perhaps the conservative and dogmatic approach of stratigraphers mandates. We find that we meet all of those in spades. And so we're now looking at rocks that can actually carry this label. Then it gets political, because, for example, all my Chinese colleagues want it in China. All my American colleagues want it in the States. And, whatever. It can be a big deal in terms, but we do have many candidate sites. The geologists typically enjoy the idea of having the boundary in carbonates and to have it as marine. And that's just because so many of these things like the Devonian and the Mississippian carboniferous, many of these things are based on the marine carbonate record. So, okay, so we have to get a coral head, a coral reef or something, but we can do it. I mean, the signal's fine. If you want a marine carbonate, we'll give you a marine carbonate. We can give you just about any kind of geological deposit that you would like. But the difference is, the real difference is that now we have an organism that happens to be a bipedal great ape with an expanded cranial capacity and furless pelage. That is the only organism that really cares about any of this stuff. The only one that has the wherewithal to care enough to break geological time into constituent units that can be reproducibly identified and mapped. And this time we're being tasked with doing that for an interval, which is the consequence of our own doing. And so I just spent an hour trying to tell you that, hey, you know what? The Anthropocene is just like the Cretaceous, just like the Jurassic. Let's just go forth with this. Well, actually, it's not. Again, those movies about the Jurassic, that's a bad example. But people aren't writing death metal lyrics about the Mississippian or the Landovarian substage of the Silurian. They're writing death metal songs about the Anthropocene. There is a cachet. There are many aspects about this which to some traditionalists seem objectionable. And so we've had this scientific decision or political statement, stratigraphy or pop culture, the Anthropocene. These guys are so full of themselves. They're having too much fun getting press and being published in fancy journals like Science, the paper that I sent out that's been cited a couple of hundred times. And it's so insidious. I didn't set out to do that. I would argue that, well, okay, for once, there is interest from the broader community in something which is geologically sourced. Isn't that a good thing for the science of stratigraphy? Isn't the recognition of humans' impact in a dispassionate, unbiased way as creating an inscription in the geological record, isn't that worthwhile? And you know what? We have had success publishing these things, and these things have been published all over the place and cited, and I've been on the radio and the TV, and I do French and I do English, and that's cool. But it was nothing we set out to do. Maybe we unknowingly opened a can of worms. But I find it objectionable that we've been accused of bandwagoning and conducting ourselves in any way that is short of the kind of scholarship that this mandates to do it right. Because one of the things I didn't tell you about SCS is that once you get one through, there's a moratorium on any revisions for 10 years. And in some geologists' minds, 10 years can be an eternity. And that's actually a terrible attempt. I'm going to stop right there. And so I'm not going to get into the details here, but I've backed off a little bit because there's been acrimony on some of these critiques. But Gifford has agreed that he can maybe post, if you have a Dropbox, he can post a PDF of my files. But I'm actually going to stop here. Thanks tons for your attention. I know I went on too long, but I'll gladly field a few questions.
Okay, why don't we open it up for questions and from the crowd? I do have a copy of these, so I'll pass those over to Joe and he'll put them up and people can both view the talk on the recording or they can slip through the slide deck and look at that. So how about from the community out there? Do we have some questions for Alex?
Go ahead, Carol.
Yeah, so I do have a question. So I thought it was a great talk. I really enjoyed the fly ash particles. I thought that was especially salient. But I have a question about if, let's just pose for the sake of argument, which I don't think is utterly implausible, our species goes extinct at the turn of the next century. I don't think that's utterly implausible. But if that happened, would the deposits for the Anthropocene period be geologically have a long enough time period that in say, let's say 100 million years, they would be still present and globally enough to be recognized as a geological epoch? I mean, yeah, right.
Absolutely.
Okay.
I think categorically, I mean, think of our industries, think of our cities. What are our, there's some some examples on Netflix of what things look like after the human extinction and stuff. We've already manufactured enough concrete to put a skin 2 millimeters thick over the entire planet. And so when our cities and freeways, when it happens, particularly in urban areas, but even in rural areas, even at the bottom of the ocean, things like the trawler, the otterboards on trawlers that create these scours. And so if you go to any shallow continental shelf, for example, the Grand Banks or the Flemish Cap, or anywhere really in the world, because every continental shelf is being fished, you have these trace fossils, these scours on the bottom of the ocean. This is a very lasting, and then there's both the intentional stuff like our buildings, and then the less intentional stuff like, all the pollution and the carbon imbalance from creating those cities, that together create a formidable record. The idea is we already have that record. And so when I'm quoting the middle of the last century, it's kind of like when you say I'm trying to define the Devonian, I'm going to go look for the earliest occurrence of the graptolite or the fossil that is indicator of the Devonian. With the Anthropocene, so too, we'll go to the earliest point, which I think is a point in the very, very recent geological past, right around Trinity, 1940, the plutonium spike. That's where it begins. But the bulk of the deposition is yet to occur. But the first inscription, really the first geological inscription of a planet that is now dominated by one species, that species being our own, that would be that golden spike. And I would argue that even from then to now, we've created a world that if 100,000 years from now, whatever, we're 2 million years, say 5 million years, because that average species duration, the Quaternary, is about 3 million years. And so when species are gone, when our species is gone, say another species comes and looks at the Earth system and starts taking cores in the way that we do, when they go through the 50-meter asphalt horizon, they're going to go like, oh my God, what happened here? And then when on top of that, there's styrofoam and chlorofluorocarbons and mercury and so on, it's going to be it already is, say, take a core through landfill.
So can I have just another quick follow-up question? So how would you distinguish that from something like the KPG boundary, where initially people didn't know what length of time period it represented, right? They thought, well, maybe this is a time period when something catastrophic happened over a period of maybe, Yeah,
I'm really glad I paid you $5 before the talk to ask that question. And so, no, just kidding. The boundary carol for the stratotype for the Cretaceous Paleogene boundary is in a locality called El Kef in Morocco. It's beautiful, beautiful rocks. And there's actually a chemical anomaly where the extraplanetary platinum group element iridium is enriched in the rocks as a boundary layer claystone. Now, I live in a place where these rocks are exposed, but both when I worked in Alberta, and we actually have some pretty nice places around here, and we look for the KPG boundary. It's not that conspicuous. There's a lot of little layers of clay that thick in late Cretaceous rocks out here, trust me. And if you went to the Book Cliffs around Fruta and Moab, and you have those rocks there too, you got to be pretty good to find it. But if you start measuring the geochemistry of these rocks, it's easy to find because the iridium goes through the roof. It's going to be the same with the Anthropocene with these long-lived radionuclides. Some of the indicators like americium and cesium, they have short half-life, so they go away. But the radiocarbon one, well, that's more interesting because that's going to last thousands of years. And indeed, the plutonium is going to last for indeed tens or for much, much longer, basically be a permanent inscription and so Trinity is just the first time you're going to see that that nuclear testing spike. But this has nothing to do with any political connection or anything to do with the Cold War and with the Manhattan Project. You know, it just so happened that that episode in Earth history put something into the global environment, which ends up being a very, very useful temporal marker, just as the bolide impact 65.5 million years ago left an iridium trace, which serves the same purpose.
So just final follow-up question. Supposing the KPG boundary had lasted a lot longer, we hadn't discovered it was this kind of virtually instantaneous event, which people were debating at the time when the Alvarez, I mean, one of Walter's question was this, and that's one of the reasons that he asked his father thought of looking for iridium. You know, was this a short period, or let's look and see at the rate of iridium falls to the earth and see whether it's actually evident for a long period. Had it been a long period, would you have changed your mind and called it an epoch?
Once again, it's a great question because it really sets me up, I think, personally, in a very, very favorable light for my own arguments, since I really like it when people do that. The human experiment is long, right? So, you know, your first mammoth bone is Clovis or whatever, you know, over 10,000 years ago. You still have to find the boundaries somewhere. It looks like with the KPG, you know, there's no dinosaurs anywhere near that KPG boundary. It looks like in Alberta, you know, where we have, you know, basically like fields full of ceratopsians and hadrosaurs. They're everywhere. But, you know, within 200,000 years of the boundary claystone, there's no dinosaurs. You know, there have been some false starts, but it's clear that the KPG organization, reorganization of flora and fauna, the ocean chemistry, it's not one moment. It's just that one moment, the impactor which creates the marker, that just provides a very, very convenient, like, there's a good marker. So the reality is the geological timescale isn't perfect. It's actually a masterpiece of compromise. You got to put the boundary somewhere. You know, try putting the boundary at the last dinosaur. You know, it's pretty hard to do. It's a lot easier to look for the enriched iridium. And actually the enriched iridium comes along with a spike in ferns, in fern pollen. And so that's, you can actually do that. That's better than dinosaurs. Well, guess what? The dinosaurs are these big, massive animals. They don't respond in the same way as, you know, they don't respond in real time. They have evolution and behavior. They have all this weird stuff that we don't know anything about. And they're so big, there's relatively few of them in relatively few rocks, yet, you know, anywhere with a KPG is going to have an iridium enrichment. It's the same a little bit with the Holocene. The processes that contribute to this notion of Anthropocene were initiated a long time ago. It's just that now we have this convenience of a good stratigraphic marker, which we can opportunistically seize. The big problem, of course, and this is, again, is political, it's very hard to find standards for the measurement of plutonium using the technique that we use, which is inductively coupled plasma mass spectrometry. We absolutely need standards, and for military reasons, you know, I mean, you probably can buy a plutonium standard from Iran off the web, but, you know, whether you can bring that into an NSF-funded lab to calibrate your machine is another question. We can't do that here. There's only a few people who can do the measurement effectively. You need to have, I mean, you're still measuring parts per billion, again, much like the KPG with the iridium. It's like, oh, iridium spike, yeah. Like, well, yeah, look at the unit. It's like iridium spike, yeah. You know, 10 parts per billion instead of 0.5 parts. You know, it's not, yeah, I mean, we can do it now because we have geochemists like Giff who are great at measurement, but there's some subtlety. But I still say that with the Anthropocene, we're going toe to toe with the KPG and other intervals. We're not saying that things happen overnight. We're saying that the chosen marker was deposited discretely in time, and you know, a pretty good placekeeper for this sequence of transformations by which humans were just part of the landscape. And then we had this nice interglacial, and then we created animal husbandry and started trading things and language and culture, and that's fine. And then at some point in the 20th century, we actually took hold of the knobs of the thermostat of the deep ocean and the radiative forcing of the atmosphere, the particulate load of reflective and refractive materials in the atmosphere, the composition of water, the trajectory of waters. You have a colleague, Jai Savitsky at CU Boulder, who works on reservoirs and the alteration of the hydrological cycle. You know, groundwater depletion in Florida and Bangladesh that you can measure from satellite gravimetry from space. I mean, you know, one thing is we have great measurement. Space more, yeah.
A quick comment. You know, one of the peculiarities of the geological timescale is that the time between intervals gets shorter and shorter the closer you get to the present. So there's no sort of equalizing. The Cretaceous is about as long as everything else after that, and so what seemed, for those people who are opposed to an Anthropocene marker, the last marker is the Holocene. It's an established and agreed upon, and yet if you went to many places around the planet, you would have a very hard time saying there's a clear, at 11.7 Ka, that there's a clear marker that says, aha, there is the boundary. That the Anthropocene boundary is more explicit than an established boundary between the Holocene and the Pleistocene. Would you agree with that?
Yes, I would. I would. I couldn't have said that more eloquently. Yep. And so just in stratigraphy, there's actually been some ongoing, the Holocene itself has been subdivided into substages based on relatively minor climate features. So for example, the early Holocene, which you think was a little bit warmer, the middle Holocene and the late Holocene, where we have neoglaciation, which seems a little bit cooler. And these have recently been proposed and ratified as substages. And I find it's confusing and miring because the low-hanging fruit in terms of the biggest change, the biggest demonstrable change, is not the subdivision of the Holocene into the North Grippian and blah, blah, blah. It's the Holocene Anthropocene, where, you know, really from the perspective of our species or any species, and the commensurate changes of, you know, living in a molecular age, living in an internet age, living in, you know, having this technosphere which produces a fossil record. You know, and I've got nothing against gnawed mammoth bones. I love that stuff. But, you know, now we have, you know, like, I don't know, cell phone carcasses, you know, things like that forming the fossil record. To me, it's a bit of a no-brainer, which is perhaps why I reacted poorly, if childishly, to you know, some of the most acrimonious critiques.
Anybody else? We should probably wrap up pretty soon, but anybody else out there besides Carol and me who talk too much? Anybody else? I mean, we have some GRAs on here. How do you folks have some questions or thoughts on this? It's not a trivial. Yeah, I think it's trivial where we mark it in some ways, except geologists who get carried away on that. But the recognition of the dominance of our species is a pretty hard thing for some people to swallow. And so I'm wondering, like, from the historical perspective or another perspective, how do people feel about that?
I got no. There are a lot of people who think that human beings don't have the capacity to change the planet. That it's so big. It's actually the planet's pretty small in celestial terms. The sun's about normal for a star. What I'd say is that, you know, it's not the first time an organism has changed. So, you know, when I began, I spoke a little bit about Earth system science and the way, you know, really geologists, you know, this is kind of weird because geologists always use fossils and fossil record. The fossil record is very, very important for this game of stratigraphy. But geologists always, you know, up until maybe 25 years ago, underestimated the role of biology in fundamental Earth processes. And of course, it was only with people like Lynn Margulis and Andy Knoll, and you know, people really at the forefront of the thinking, pushing this sort of Gaia type notion, which I guess today we'd call more efficiently geophysiology. The advent of Rubisco and photosynthesis produced a waste product of free oxygen, which basically presages the evolution of all of eukarya, which is all respiratory organisms. And yeah, that's a pretty big implication of life.
And these were little itty bitty things that did it.
Yeah, that's why I say it's a microbial planet. When these itty bitty organisms, photosynthetic organisms, started colonizing the land, and then a couple 100 million years later formed forests, we had a new repository for carbon in the Earth system. So basically taking carbon that otherwise would accumulate in the atmosphere and putting it in an archive. Soil carbon, you know, next to carbonate in the ocean, it's the largest, you know, there's 200 times more ocean in the world's, 200 times more carbon in the world's soils than there is in the atmosphere at present. It's one of these deep repositories. Essentially, when that began, you know, maybe 350 million years ago, it essentially puts a ceiling to how high carbon dioxide can get in the atmosphere, because it's continuously being sequestered by the organisms that then produce soil carbon, all the photosynthetic organisms. And so that's another example of, you know, life taking a turn that fundamentally changes the, you know, and one of the incredible things about Earth is not that Earth is Earth, but that Earth has remained livable, you know, sort of in this window that enables life, that has been in that window continuously for over 3.5, almost 4 billion years. Is going, you know, and there's no evidence that life evolved more than once. And that's remarkable stability. And I think it's that stability that then begs that there be feedback processes inherent in the Earth system that regulate. Those are all what we call negative feedbacks, the ones that regulate the stimulus of, for example, ramping up CO2. Other planets, you know, like Mars was probably habitable for a spell, but then got too cold. And so we have this remarkable stability, not on timescales that are much greater than our own on Earth, and life has a key role. It just so happens that now we have another organism. So, you know, maybe every couple of 100 million years, an organism comes around that stirs up the pot and changes the whole course of the whole planet. And now we just have another example of that. It's the first time it's been a vertebrate, certainly the first time it's been a great ape, but it's not that different. And you know, there are many other examples. You know, for example, when the first burrowing organisms rose in Ediacara, which is the end of the Precambrian in the global ocean, there were tremendous implications for the chemistry of the planet, because of oxygen now is able to get into the sediments where it hadn't been before, and that engenders a whole suite of chemical processes that change the nature of the rock record. It doesn't happen every day, but life occasionally does reshape the course of geological history. We just have to accept that now it's happened, and it's happened by the only organism that cares enough to describe this.
And I think one of the more eloquent ways of stating the human role was from Roger Revelle in 1957, where he says, human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past nor reproduced in the future. Within a few centuries, we are returning to the atmosphere and the oceans, the concentrated organic carbon stored in sedimentary rocks over hundreds of millions of years.
Yeah.
And that is the trigger that explains everything else in the Anthropocene, I think.
Yeah. Charles David Keeling's postdoctoral advisor.
Yeah.
So it just goes to show it's the same pedigree.
Yeah. Well, how about it? Have we at least got a start here to thinking about the Anthropocene and how we might move forward and look at it from different angles? We got the geo perspective, which of course Alex and I both think is the fundamental one. A good, yeah, Kieran.
Yeah, so I'm not a scientist, but I've been reading a lot about beavers lately, and since you're from Canada, I've wanted to ask you this question. Beavers apparently really reshaped the ecosystem of the Earth for millennia too, and I was wondering if we should, rename, a geological marker, Castorocene or something like this. So if we follow that idea of Anthropocene and other animals changing our environment for noticeably.
Well, it just happens to have been humans. It could have been any other organism, and it could have been another mammal. Had things have been different and beavers had, I don't know, different fecundity or different species diversity, and they'd sort of like started taking over the planet the way that we have, I agree with you that there could be a Castorian interval. Similarly, when you look at things like, how keystone species like wolves in Yellowstone, or in certain ecosystems, it's pollinating insects, or, whenever you deal with ecosystem structures that have keystone species, as we call them, if one of them all of a sudden takes off and no longer becomes a keystone species, but becomes, the uber species, the dominant species at a planetary scale, then yeah, sure. If mosses and if club mosses and lower plants did it in the Devonian, they just sort of evolved, changed the carbon cycle forever, and ushered in a new system where CO2 never rises above, say, 1,000 or 1,500 ppm for the next 300 million years. Any organism can basically set off one of these dramatic events under the right circumstances. And it just sort of turns out that, I haven't really thought about it that much. There's only a handful of instances where I can think about, individual species who've really changed things. Usually the stochasticity of things like asteroid impacts, or the longer scale influences of, altering planetary tectonics. For example, if you have ocean currents that can go all the way around the equator or not, it's usually one of those sorts of things which ushers in these new periods. But it can be life, it has been, and it could be again. The beavers haven't done that. When Canada sent beavers to Argentina, they almost did, but they didn't quite take over the world. So I'm open to that. It's just we still have to look at the data that's available, and the data that's available for humanity is more resounding than that of the beaver ones, which are seem to be more local.
There's rabbits in Australia.
Oh yeah. Yeah, there's a lot. But one of the things about these markers, and it's another really good dovetail point, is that these markers do need to be globally recognizable, and the plutonium is very good for that. And so in some of these intervals that I'm interested in, like Ediacara, the terminal Precambrian, you look at the rocks in Newfoundland, and you look at the rocks in China, and you look at rocks in Australia, which is where the stratotype is, and it's definitely global. Things pretty exciting period. It's every bit as exciting as the Anthropocene from a geologist perspective. It's just all of a sudden there's attention. All of a sudden, there's musicians and artists and stuff using the term, and some academic geologists actually demur from that. They feel it's like, oh well, I just heard an economist say Anthropocene, or, you know, or a legal scholar. It's like, you know, that's not right. Or, you know, and I'm like, no, you know, like the bigger the better. You know, if we can make any aspect of the earth sciences, particularly our own fingerprint, more accessible and more uniformly defined and more understood, I think it's a move forward. We each, it's great to have multidisciplinary fora, because we each have disciplinary biases, which unfortunately we carry.
Any other comments or questions? I see in the chat, Kieran, we asked whether you'd read Ben Goldfarb's Eager.
It's just it's a great accessible summary written by a journalist of the beaver phenomenon.
Oh, okay.
It's really good.
I haven't, I haven't read that one, but what I've read is that, you know, beavers for millennia completely changed the hydrology of the planet through the regulation of the rivers and all that. So their impact was
in the boreal,
global.
In the boreal, and boreal is really, really important. But you know, there's no beavers in the tropics. In the tropics, you know, mole per mole in terms of where, you know, a lot of the action is in the tropics, because the tropics it's the one part of the planet where you have excess energy, right? Basically, you're so close to the equator, you get so much energy in the tropics, and then that energy gets put to a variety of things, like setting up intertropical convergence, setting up ocean currents and stuff. And so that, yeah, really a lot of things are dialed by the tropics, and then secondarily dialed by the poles, because the poles have this capacity to be almost entirely reflective in the surfaces of snow and ice. And that, yeah, the boreal is hugely, hugely, hugely important. It's one of the largest, and the beavers are fundamentally important to boreal hydrology. There's no question there.
Thanks.
I just was going to say from a more thinking about the implications of the word than sort of the evidence for the era. You know, when you had your slides up about kind of the history of the Anthropocene in general, sort of and also in the way you talk about it, you know, there's this language of domination and control and sort of, you know, and so I don't know, I come at it from both sides. On one hand, I think it makes sense to have it human and species centered, especially because there's just a plethora of evidence, right, that all relates to human activity. Like you said, I thought it was a really interesting point about how, you know, there are certain like points in the nuclear age that are really great, you know, for markers or for signals, but really it's just sort of this preponderance of evidence. And so I think it makes sense to try to, you know, to use humans as the linguistic center. But I'm also cautious of that, because I think a lot of what's going on is not under our control. You know, it's not our intention in making plastic to have it, you know, become part of our bodies, right? So anyway, I don't know if that's something that you as a scientist also deal with, like trying to think about, you know, the whether humans actually have domination over nature and whether we want to keep that, you know, language going, or whether it's actually kind of a clear thing for you.
Well, domination is, you know, I use that essentially to state that that's the way it is. And so and I know that sounds facile, but, you know, hear me through, and that, you know, we know that CO2 emissions from, you know, say fossil fuel emissions, from fossil fuel combustion and cement manufacturing, we know that that's, you know, we know where that stands in terms of natural biospheric respiration. You know, we know that we're capable of influencing the chemistry of the planetary system. We really are dominating the system, and I don't think that's arguable. It's just whether or not that is sufficient to provide the geological record that we need then to identify it with. I sort of go back and forth and stuff. you know, there is something just different about the unrelated scale of the human enterprise in, say, the last 2 generations than anything that was before. You know, it's technologically fueled, and it truly has led to the human domination of so many geochemical, biospheric, and physical processes. I haven't found a better term. I agree, it does sound a little self-important. I guess I really do try, when I think about that question and that comment, I guess I really do try and look at it as much as possible, completely dispassionately, without any sense of attribution of good Anthropocene and bad Anthropocene. In fact, I don't like I don't like the term a good Anthropocene and a bad Anthropocene as, you know, the outcome of say decision making in the present, because for me, it's already there. You know, for me, for what, you know, I'm trying to limit myself to talk about the things that are already inscribed, already exist, that I just haven't done a good enough job to compel, you know, the scientific community at large and the broader community that this is worthwhile doing through the auspices of my subdiscipline. So it is tricky. But if you just look at it purely objectively, especially when you start reading those papers from geochemistry and stuff and environmental toxicology, when you compare, like, you know, natural fluxes of just about anything with the post-industrial flux, it's frightening. And a lot of these things are still accelerating, you know, like we thought with the Montreal Protocol that, you know, we had CFCs under control. Well, there's fugitive sources somewhere in North Korea or South Korea, or, you know, again, not pointing any, you know, we know there are fugitive sources of these ozone destroying chemicals somewhere in Southeast Asia, because we have amazing monitoring of atmospheric chemistry. And yeah, for everyone that's being sort of managed and stuff, you know, we haven't been able to manage carbon dioxide emissions despite trying, you know, going back to Roger Revelle and Charles David Keeling, and certainly Jim Hansen, and that's the mid 80s. And the year-over-year increase of CO2 is as high as it's been in my lifetime, you know, 2 to 3 parts per million a year, you know, even during the pandemic. That's like, yeah, so these are just factual processes. I'm not trying to sound as though I'm getting all depressed about it.
No, and that's interesting too, because it sounds like I hadn't really thought of this before, but it sounds like you're kind of making a distinction when you use that language between like scale and actual effect and intentionality, right? And a little bit at least. And so that's something I hadn't divorced those two really when I think about those kinds of words. So it's just something.
Yeah.
Everything, I agree. I mean, from my historian perspective, I agree with what you're saying. And just thinking,
you know, we don't, language. You know, I hate to say it, but, and I'm not going to speak for GIF, although I imagine, you know, I don't really structure my arguments sort of formally in the way that you just, you know, I basically just say it the way I see it according to the data that I've observed. And I just don't try and, you know, veil any, I try and veil as little as possible in the vicissitudes of my discipline. And I think there are real scientists who do the exact opposite. They will use their discipline to you know, to hide dirty secrets and stuff like that, or biases and so on. Not everyone, but it does happen. Which is why, you know, crowds like this, multidisciplinary. I mean, I do use the jargon. I do use examples from the rock record because I have to, because that's what I know. But I do think it's absolutely essential that the concepts and indeed the observations and the data and all their sources and stuff like that are broadly accessible.
You know, one thing I don't think there's any even shred of evidence that there was ever an intentional goal by humans overall to change the planet. This was never, and in fact, one of the difficulties in trying to get people to pay attention to what's going on is that so many people say it's impossible for us to do that. Even, I mean, they were not willing to accept that. So I don't see any and yet what you see now from the engineering side is, well, maybe we should take engineering tools and try to use those to geoengineer the climate system. And so that's in a way that to me is an intentional, well, I think going back to CFCs that Alex mentioned there, to me, the one most hopeful piece of evidence about being able to mitigate what's going on is the response to the ozone hole and the chlorofluorocarbons that did it, where for the first time in the entire history of the planet, representatives of every single group on the planet got together, agreed there was a problem, agreed it was something we were doing, and agreed to reduce it. And although it's not perfect, it was a huge success. And so but that's the only example I can think of where the whole planet got together and said, we are changing things and we'd better do something about it. And so that's an intentional move to mitigate damage that we were doing on a global scale because it was going to negatively impact every life on Earth.
But note that's not the same as geoengineering. That's an omission.
No, right, yes.
Geoengineering worries me because it's the same kind of interference and we don't really have an understanding of the ramifications.
Yeah, absolutely.
Much easier to do an omission and bring things back than to try to throw something into the atmosphere and hope that it's going to counteract. You have to have a really good capacity, and we don't have that yet to model the whole ecosystem.
Yeah, so really the transition to renewable resources at the reduction of fossil fuel emissions is the same sort of thing. It's not geoengineering, it's an emission, a reduction rather than an engineering solution.
But I wonder if the earlier comment is Angela, right? The earlier comment?
I'm Amelia.
Amelia, sorry. I'm
That's
really
fine. There is an Angela, but
I've always been terrible with names, but I didn't check I usually check ahead of time. So I wonder if Amelia's comment might be useful in this following sense, that some of the people who are even the geologists who are really hostile to the Anthropocene might be thinking along the lines that you suggest, that this semantic difference could be driving a debate that is really people really talking about different things. As we philosophers like to say, we're really not using language with the same meaning. And you might not even be aware of that. It's just something to think about. And I don't know whether Alex would have some insight into this, but is it possible that this intentionality aspect and this idea of dominance that you brought up is kind of being tacitly brought into the debate, and there's a misunderstanding rather than an actual, what we philosophers say in logic, a disagreement. There's an actual misunderstanding rather than a disagreement.
Yeah.
Well, just to clarify slightly, you know, what my concern comes from is more that there is a long history of various groups of people really believing that humans have dominion over nature and then acting on that, right? So the geoengineering is exactly kind of what I had in my mind, you know, what cautions can we learn from the past and say, okay, you know, we have this, you marked it back to the 1700s, I think, and I think arguably, depending on where you're looking, it goes back thousands of years, right? This particular type of language. And so today, that's really where my concern was more coming from. Just how does this impact what we're going to do today? And if we're going to say, okay, great, now we have dominion and we'll make this left turn and do this completely new thing, and what are the ramifications of that? So anyway, just to be my point a little clearer.
Yeah, no, I mean, if that's one of the consequences, you know, I think, yeah, I've heard sort of reiterated in different ways. It's like, yeah, I think having a common definition that we can all agree on is a step forward, I think. And but
it might not just be about definition. It might be about people unwittingly having different concepts.
Yeah.
Implicit, which are, you know, causing what appears to be a disagreement. It's merely verbal. That would be the concern I would have. But I don't know whether this is the case. I would actually love to be involved in that group that you talked about.
About geoengineering, I think from my perspective, geoengineering is a red herring. The first reason being that, well, it's something yet to occur at a large scale. I mean, they've been putting silver nitrate over fields in Southeast Asia for decades, but and seeding clouds, but at a planetary scale, it hasn't been done yet. But it's in the future, so it's no longer we're not seers, we're environmental historians who use the rock record. So whatever happens in the future doesn't really matter. So our data has to be robust enough that we can stand on what's already inscribed in the rock record. The second thing is that the geoengineering, irrespectively of whether it has a quote unquote favorable or non-favorable outcome for, say, the climate crisis or something like that, that's immaterial to the argument. It's still going to contribute one way or another to the burden of materials and processes and their ultimate integration into the rock record. It's still part of the story, irrespective of what the actual outcome is going to be.
Yeah, Alex, something I've never run by you, but our topic is the origins of the Anthropocene, and my thinking lately has evolved a bit to say the origins, like the very starting point, was when humans obtained the ability to have fire on demand, and that no other organism on the history of the planet, lots of organisms utilize fire to hunt off it and all, but nobody had fire on demand. And really, once we got fire on demand, you could get steam engines, you could get gasoline engines, you could do that was one threshold change that doesn't leave a rock record of it, but the rock record, the 1950, if we call that the threshold, I'm fine with that as being the point where we can see it. But I think the origin is 500,000 years ago when we learned that little trick of making fire. Yeah,
but you know what? It's stratigraphy is a conservative science. Yeah. Not politically conservative. It's deliberately conservative because you don't want to proliferate new terms and you don't want to populate this with things that then it's like, oh God, why did I subdivide the Holocene into 3 different substages? You do not want that. And so it's sort of intellectually, it's almost a sort of closed door. It's not the most open environment, the world, the deep inner workings of the stratigraphic sciences. So you have to have a good case, and you want to try and make it well. And so typically you don't look for the earliest occurrence, because there's something that we call in paleontology the Signor-Lipps effect, which has to do with finding things, and your chance of truly finding the beginning or the first organism. Basically, it's never going to happen. Or the last organism, last individual of a particular organism. Yeah, and so basically, you want to look at the sort of the acme. Once it's well established and diverse and well preserved, or whatever the case may be, to have a body of evidence, not the one instance. And I think that the case of the KPG, to go back, the iridium horizon does that much better than the highly diachronous nature of, say, the dinosaurian fossil record. The iridium does it nicely, and the fern spores do it very nicely in ways that the bone record simply doesn't. Not because I have anything against dinosaurs, I love them, but because they're big and clunky. They don't have the, it's good if you're really small, really abundant, you get disseminated by the atmosphere, then you have these, you immediately have attributes to create these sort of blanketing horizons that will be indeed global in nature, when all is said and done and the geologist starts digging and measuring.
So what's interesting about the iridium, though, it's not just iridium, it's the shock quartz, it's the tektites, it's the glassy spherules. There's just a lot of stuff that just wasn't, you could have really done without the iridium, I think. Because not all meteorites are rich.
Well, the tektites aren't global. They're the impact quartzes and stuff like that. That's fine if you're within 500 kilometers of the Yucatan Peninsula, but they're not global.
They aren't? I had thought that tektites, no. Just the
No, it's a radial pattern around from the Shikulub locality.
That's interesting. That's very
yeah. Yeah. Well, similarly, you know, the trinityite, which is the equivalent from Trinity. It's one of those anthropogenic minerals. You know, you only find it in New Mexico. You don't find it up here in Manitoba.
It's really interesting.
Well, I see we're sort of slowly having attrition on the group here. But I think we should thank Alex for a stimulating talk. Got a lot of people thinking about stuff, a good way to kick off the Anthropocene, and we'll look forward to those of you who are going to continue, which hopefully is most of us, to bi-weekly. We're going to be now looking at individual papers through the rest of this term. Carol, anything you want to add here at the end?
Sorry. No, I think this was a wonderful talk. I really enjoyed it. It really does connect with my interest in classification in the historical sciences, not just mineralogy. And in fact, I just wanted to say, Alex, I would love, would they like a philosopher in that group that's thinking about classification in the Anthropocene?
No, we have representation. Yeah, not the idea of the broader.
Yeah, it would be really fun for me to think about it from a philosophical, definitional category.
No, I can send you the contacts of, you know, Jan and Colin and stuff. They're very, very approachable people.
Yeah,
they're pretty cool.
Really interesting, because I think it expands the stuff I'm doing now in mineralogy. It really fits in with that. And I would be interested, you know, being a fly in the wall at least.
Yeah, that mineralogy stuff actually sounds as though it could have possibly some pretty interesting pedagogical content. I'm just thinking about teaching.
It really does. In fact, the paper, as soon as we have the official PNAS acceptance, I'm the first author and Bob Hazen's the second, I will be happy to share it. I'm going to actually give it to him, I think.
Cool, yeah.
But we're still waiting for the official, but it does fit in really in an interesting way with that, which is why I'm so interested in these timescales.
Yeah, I know that in the American Mineralogist, there have been, I can think of there are at least 2 papers on these anthropogenic minerals, and you know, the ones that come out of weird chemical processes and stuff, and there's some pretty crazy ones.
Yeah, it is, and it turns out 70% of the minerals on Earth are at least biogenic. Really surprising. So just from the planet itself, it didn't have any biology. It would be a really different planet.
Yeah, absolutely.
Amen.
Yeah. Okay, folks, thanks so much.